Well, Lake Chelan geology, right? You came to listen to a lecture on Lake Chelan geology. Let's start by saying this. Let's say you've got a friend on the East Coast. His name is Jerry. And Jerry calls you out of the blue and he says, hey, good news, I'm going to come visit you in Washington. I've been hearing you talk about all this geology out in Washington. I want to see it firsthand. And you're like, okay, Jerry, sounds good. He says, I know you got a lot of different kinds of geology out there, right? Yes, we do, Jerry. He says, great, I'll be there on a Tuesday. And you're like, you'll be here on a Tuesday? He's like, yeah, I'm going to come for one day. I want to see as much geology as I can in one day. Where would you take Jerry? Where would you take Jerry from New Jersey? Rainier? Dry Falls? West Coast of Washington? You'd have a theme or two, but you wouldn't have the whole smorgasbord that you need to give Jerry. I think I would take Jerry to Lake Chelan. Does that surprise you? There's more up there than a lake. Here's a laundry list of all the wonderful geology in the Lake Chelan area. Canada ice sheet, alpine glaciers, third deepest lake in the United States. The Columbia River, glacial Lake Chelan. Ice Age floods, flood basalts, exotic terrains, metamorphic rocks, granite batholiths, and oh, by the way, the biggest earthquake since the Civil War in Washington. We're going to cram all that into tonight's lecture. And I want to do it in 3 parts. Yeah, we're going to start with the lake and how the lake formed. That's probably why you came. But I want to do more than that. After that, we'll do a little bit on the bedrock. There's beautiful bedrock up there, visually beautiful. And I want to talk about that earthquake as well. And then we'll look at the visuals and go through the same 3 guys again. You ready? You are? Okay, let's do it. Where is this lake? Ellensburg is here. That's you, the Hal Holmes Center tonight, right, on this beautiful winter night. We're going up here. It's a lake, Lake Chelan. It's 50 miles long. It's a mile wide, long and narrow. And you go, okay, that's kind of weird. Well, we got Lake Roosevelt that's long and narrow, right? How did that form? Well, we put a Grand Coulee Dam on, right? And we backed up the Columbia, and that's why Lake Roosevelt exists. Banks Lake, that's long and kind of narrow. What's that? Build a dam, pump a bunch of water into the upper Grand Coulee, you got Banks Lake. Is Lake Chelan the same story? Well, there is a dam in Chelan. They built it in the 1920s. It raised the level of Lake Chelan by about 20 feet. But that's not why Lake Chelan exists. Lake Chelan is the 3rd deepest lake in the United States. You don't get a lake like that deep, by just damming a river, right? Crater Lake in Oregon, deepest lake in the U.S., almost 2,000 feet deep. Lake Tahoe in Nevada. And number 3 is us, Lake Chelan. How did that thing form? It's deeper than Lake Superior. It's deeper than Lake Pend Oreille up in northern Idaho. So what is the story? If you guessed glacier, you're right. But if that's all you want, you just a self-satisfied nod, okay, yes, yeah, Lake Chelan was formed by a glacier, we're moving on. That's not enough for us tonight. How did this lake form in the Ice Age? Which glacier was it? Where did the ice come from? How thick was the ice? Did the ice come down from wherever multiple times? Is it possible there was more than one glacier? Because we need to make a deep hole. This lake is so deep that the bottom of Lake Chelan is below sea level by hundreds of feet. Freshwater, Lake Chelan, a hole that's below sea level. Who the hell did that digging? Ice, but when and why and how? All right, so let's look in the neighborhood. The drainage to the south is the Wenatchee River. The drainage further south than that, let's put Wenatchee here. The drainage to the south of that is the Yakima River, coming right past this building here. Are there lakes in the Yakima River drainage and the Wenatchee River drainage? There are. There's a little lake upstream of us, Lake Chelan. That's the result of a glacier. Is there a lake in this Wenatchee River drainage? There is. Lake Wenatchee, the result of a glacier. But those glaciers let me use white here. Those glaciers are fingers of ice, alpine glaciers coming out of the mountains. And so if we're looking down on an alpine glacier, this is Geology 101 now. If we're looking down on an alpine glacier, this is a map of an alpine glacier, you got it? If we do that, and the glacier brings a bunch of rocks down and drops them and makes a ridge, that's called a moraine, made out of loose glacial rocks. And then if we melt that ice back, we are left with that moraine, and we can get a lake ponded behind that glacial moraine. It's kind of like damming, just like we were talking about before, a natural ice age dam of moraine material. And so that's the story here, that's the story here. But we don't have a Lake Chelan. The Wenatchee Valley doesn't have a Lake Chelan. We need that deep hole. Is there something else going on? There is. Lake Chelan is not the result of an alpine glacier coming out of the mountains. And that's what I assumed up until a couple of years ago. I teach Washington geology for a living, and I just assumed there was alpine ice coming out of the Cascades making Lake Chelan. It's not true. And I'll show you the evidence it's not true. Well, if it's not an alpine glacier, what other choice do we have? It is ice, right? Yes, it is. What do you got? Right. The ice sheet. We are far enough north in Washington to have an ice sheet come down and somehow create Lake Chelan. So here's the ice sheet. Here's the ice sheet. Here's the ice sheet. This is the Canadian ice sheet. This is the same ice sheet that's over most of Canada. This is the ice sheet that came down to Wisconsin, came down into New England. And this is the ice sheet during the Ice Age. Multiple advance and retreats, by the way, not just one. But each time we advanced this ice sheet, it got over Seattle, 3,000 feet of ice over Seattle. That's the ice sheet. That same ice sheet is thousands of feet thick over the Okanagan in upper northern Washington. That's our topic in just a second. This same ice sheet is making an ice dam in northern Idaho, Pend Oreille, but also making the ice dam for the Missoula floods and all that. So it's that same ice sheet through this whole story. That ice sheet created Lake Chelan. So I didn't draw this well enough, did I? Because I've got Lake Chelan here and I've got this ice sheet here. So let me make an adjustment and get that ice as far enough south so that we can get it into the Lake Chelan area. Okay, we're making progress. Lake Chelan is the result of this ice sheet somehow. But you're maybe confused, and I think you should be. How specifically is that ice sheet doing that? Here's the kicker. Here's the clever idea. In Geology 101 land, you either have a continental glacier crossing flat terrain, or you have an alpine glacier, little ribbons of ice coming down a mountain valley. What happens, or is it possible, for you to take a thick ice sheet and have it invade the mountains? It is possible, and that's the key concept we want. It is rugged mountainous terrain in the North Cascades National Park. And there is beautiful evidence compiled by mainly one guy, a guy named John Riedel. We're going to meet him tonight with a little video clip. He's the glacial geologist for North Cascades National Park. Wonderful fellow. And John's work for the last 3 decades has been to find evidence of the Canadian ice sheet plowing into the mountains, not beveling off the mountains, but flowing into the mountains. And the ice sheet is so thick in places that it's literally crossing mountain ridges and going from one divide to the next. He's got beautiful evidence for this. And here's the reason we're talking about it tonight. An arm of that ice sheet from Canada found its way through a low spot, Rainy Pass. Do you know it? If you've taken State Route 20 over the North Cascades, Rainy Pass is one of those passes. There's an arm of that ice sheet. Let me do this. There's an arm of that ice sheet that crossed into the valley up lake from Stehekin. Do you know Stehekin? The upper end of Lake Chelan. So on the Cascade side of Lake Chelan, there's an alpine, wrong. There's an ice sheet arm that's coming through the mountains, through a low spot, And basically, it's an arm of the ice sheet that's masquerading as an alpine glacier. It's where an alpine glacier would flow, but it's way more ice. I've got a dimension for you. That masquerading arm of ice sheet was 5,000 feet deep. 5,000 feet of ice. An arm of the ice sheet flowing into this mountain trough. That gets our hole deep enough, especially when we can find some soft bedrock. And you go, I guess that's interesting. I was expecting more. You want more? I'll give you more. The last part of this is even more unbelievable. There was another arm of this ice sheet, the Okanagan ice sheet, that flowed up the lake. Let me repeat. Lake Chelan was formed by a glacier, not an alpine glacier, a continental ice sheet that came from Canada. But it wasn't just one advance of the ice sheet, it was two independent arms of the ice sheet coming from both ends of the lake and having a digging contest, essentially. Who can dig deeper to make this hole that's below sea level? Now that I like, and maybe you do too. And that's mainly John Riedel's story. But if it's a story, and it's against the grain, and it's against conventional wisdom, you better have some good evidence for you. I've got a bunch of evidence for you with the visuals in just a second, but let me give you one key piece of evidence that might work for you on the chalkboards here. You okay? You doing okay? Can I get you some hot tea or something? All right. Let's make a lake map real quick. We'll see how this works. It's all freehand, it's all freestyling. Bob Dylan, freewheeling geology. Oh, Lord. All right, that'll do. The city of Chelan is down here. That's a capital C. Manson is right here with all the apple orchards. There's a little kink in Lake Chelan. This is the Narrows. The lake gets narrow. There's a history of landsliding in there. And then the long stretch of the upper lake. Let's call this the upper lake and the lower lake, okay? Stehekin is up here. You take the Lady of the Lake all the way up to the end of the lake. Holden Village out here if you go take out at Lucerne. With me? The deepest part of the lake is right in here. Let's come back to that in a second. But I want to plot these two arms of the ice sheet for you, with you. And I need to show you one convincing piece of evidence that we really had those two arms of the ice sheet. And then we'll move on to something else. You ready? Here we go. Here's the arm of the ice sheet coming out of the Cascades, the ice sheet that's masquerading as an alpine glacier. And what rocks are it bringing? What rocks is this alpine sheet bringing? It's bringing Cascade rocks. It's coming from the Cascades, man. So we're going to do a bunch of this. Open circles. Open circles. Moraine, glacial till, open circles. Open circles indicating Cascade rocks, lava rocks, volcanic rocks, granites, things that we can pick up loose here and then go, yep, those are from bedrock up the valley. That's what we'd expect, probably. That even could be an alpine glacier. Here's the cool part. The Okanagan ice sheet, the arm of the ice sheet that came from the east, was bringing different rocks, was bearing different gifts for Lake Chelan. I don't have time to make them all, but I'm going to make dark, filled-in circles. Any guesses what that is? Right, that's basalt. Each of these erratics, these are erratics too, big boulders dropped by the ice. Each of these boulders is basalt. And you're like, so what? Here's why it's important. There is no basalt bedrock in the Cascades. Hardly any, essentially none. And we've got thousands of these basalt rocks down lake from the Narrows. That's the evidence that the arm of the ice sheet coming from the east invaded from the east. crossed the Columbia River, came off of the Waterville Plateau, and pushed up the lake. Why? If you go east of the Columbia River in the Chelan area, it's all flood basalt. It's layer after layer after layer of German chocolate cake, of brown lava rock, basalt. And so this beautiful transition from erratics, glacial erratics that are granitic and volcanic, light-colored volcanic, to transition here where we have these basalts and nothing but basalts, that's a key piece of evidence we had these two invading guys. How you feeling? Moving on, moving on. I don't care how you feel. We're moving on. Just kidding. I want to keep this beautiful map, but I want to get rid of the ice. And as promised, I want to say just a little bit about the bedrock, which, I had high hopes for this lecture. I thought I could do a ton with this bedrock because it's a very complicated area. And the dirty little secret is I kind of gave up. It's so complicated. I was just looking for basic messages, and I got help from people by email who know these things, and a couple guys I work with, and I can't even do basic stuff. It's so complicated. So I think what I'd like to do is at least comment on why this lake is so deep where it is. In other words, why did that ice dig so successfully just up lake from the Narrows? And then I want to highlight something called a migmatite, which I think will do better on the visuals than we are here. So let's start with, this. So schist is a metamorphic rock that is typically softer than other metamorphic rocks. So if you lose it with the rest of this bedrock stuff, this is the main message. Schist is relatively soft rock. It's not an accident that the Lake Chelan trough is the deepest where the ice is dealing with schist. It was easier digging there. Up lake, it's mostly a metamorphic rock called gneiss, which is harder, physically harder, more resistant to erosion. It's got a different story to tell. And down lake, there is something called migmatite. And a few of you are like, I thought I knew geology. I thought I was really a geology enthusiast, just like old Jerry. I've never heard of migmatite, you say. It's not common. But it's a featured bedrock piece in the Lake Chelan area. This is actually called the Chelan Migmatite Complex. What is it? Well, if you ever go to an ice cream place that serves soft shell ice cream, and you're waiting in line and you're like, oh God, when I get up there, I really got to make a decision now. What kind of ice cream am I going to get? What kind of ice cream? I don't know. Do I want vanilla? Do I want chocolate? Somebody help me out. I can't tell. I don't know. I'm going to start panicking here. And somebody just says, just get a swirl. Make it easy on yourself. Just get a swirl. Chocolate and vanilla together. And that's really what a migmatite is. It's a swirl. You'll see the pictures. I'm not exaggerating. It's a swirl of igneous and metamorphic rocks, all swirled together. And the temperatures and pressures were such that those two very different kinds of things, igneous and metamorphic rocks, can be all swirled together, just like a soft serve swirl cone. So migmatite, swirl. I want to do just a couple more things with this. Again, I had high hopes. I don't have them anymore. I've been beaten down by the complicated bedrock of the Lake Chelan area. There is more schist over here, basically downriver. Now the Columbia River's over here, right? So if we're driving downriver from Chelan to Wenatchee, we'll leave the migmatite eventually. You'll know what it looks like in just a second if you already don't have it in your head. We'll get into some schist, and downriver of that, I didn't plan my spacing very well, is another gneiss that's right above or right to the north of Wenatchee. So you'll notice that there's a lot of metamorphic rock here. Here are the basic things I want to say before we move on to the earthquake discussion. So this was supposed to be the whole part of the lecture. It's been whittled down to 5 to 10 minutes at most. Some of these are for sure exotic terrains, pieces of crust that were made elsewhere and then added to North America somehow. And whether they just came in offshore at our latitude or whether they literally came from the south, from California originally or even Mexico and then shifted north, that's a whole another part of this discussion. But it is looking like these starred guys here, I think even this one, are for sure exotic terrains. They were not made here. The ages I could give you, but they're different from their neighbors. The temperature and pressure conditions of creating these are different from their neighbors. It's a jigsaw puzzle. And every one of these is a separate jigsaw puzzle that has its own story to tell. Now, before this summer, I assumed that the Chelan migmatite complex was a terrain as well. And it may very well be, but there's a chance it's not. And that's what I want to do before I move to the earthquake discussion. I want to draw a sketch quickly of why this migmatite is very special to us, very worth our attention. By the way, we'll throw in some younger 50-million-year-old-ish granite plutons, blobs of liquid coming up once these terrains or other blocks are here. And about the time, 50 million years-ish or so, there's a beautiful set of dikes, feeder dikes, most of them mafic, meaning dark-colored, but some of them lighter-colored or felsic as well. These Eocene dikes have a story to tell as well, and we'll comment on those with the visuals. But migmatite, what's so important? What's so important? What's the visual we want for that? You hanging in there? Bedrock, man. Complicated. Thankfully, I work with a guy named Chris Mattinson, who's here tonight, and he has spent many decades on the Chelan migmatite complex. His dad studied it first back in the 70s. And this is the visual that Chris was able to pass along to many of us on a field trip recently. Let's put the Chelan migmatite complex, the swirl, into some sort of context. All right. So Geology 101 land, we have a volcano, and a volcano has a plumbing system. It's an underground room. It's full of magma. Magma. Liquid magma. Fine. And then down below that, much deeper, there's a boundary between the mantle and the crust of the earth. And usually not discussed is what's going on down below that room, in the deepest level of the crust. What's going on down there? Normally that's a, I don't know, shrug. But the Chelan migmatite complex, that swirl, is a rare opportunity to get your nose right on rock that was forming here. In other words, this is where the sausage is made. To mix, we had ice cream and now we have sausage, but hopefully you get the idea. There's something going on down here where we're actually squeezing out the rock. We're actually generating the magma that's going to fill this reservoir. And this swirling, we'll use another color, this swirling going on down here is under extreme temperature and pressure. The migmatite forms here. Last sketch for you. This is a cross-section. Here's Chelan. Here's Bridgeport. Some of you know the lay of the land up there. This is the Columbia River flowing essentially north to south, essentially. There is the potential. Let me do this differently. When we cool off this system and we turn the magma to granite, and we cool off this system and we have the swirl harden into rock, it is possible, and this is a future project that's in the work, it is possible that the granitic rock of the Brewster area and the Chelan migmatite complex are one story. Originally like this, here's the granite, here's the swirl migmatite. If we take that and just tip it on its side, perhaps that's what we're talking about here. Why is that important? Well, on most of the geologic maps today, the geologists have said Okanagan batholith, Chelan migmatite complex, two separate animals, two separate terrains, or definitely two separate blocks of crust. Chris Mattinson and some colleagues over the next 5 years are hoping to find enough chemistry details to tie these guys together. and try to make at least one small step forward to simplify and make this area a little bit more comprehensive. Last thing before we go to the visuals, I'll just do it verbally. The greatest earthquake in Washington recorded history, basically since the Civil War, we've had one huge earthquake recorded. It happened in 1872. It happened in 1872. He goes to his notes. December 15th, 1872, 9:14 p.m., estimated magnitude 7.4, someplace in the Lake Chelan area. Between 1872 and essentially 3 years ago, 2014, it was a mystery as to where that earthquake happened. Washington, especially northern Washington in 1872, was incredibly sparsely populated. Just a few log cabins, a few scattered pioneer homes, most Native Americans who are passing things along orally, of course, but nobody writing things down. There aren't even any local newspapers in 1972. You got to go to Walla Walla or Olympia to find a newspaper account. But from those newspapers, outside of the region, it was clear there was a doozy felt across the entire Pacific Northwest. And until just a few years ago, that was a complete mystery as to where that 1872 quake struck. We now know there was a beautiful discovery 3 years ago, and I'll show you with the visuals where that fault is, where the ground broke. And I'm afraid the bad news is those kinds of faults are still alive, they're still active. And so we are concerned that a repeat of something like the 1872 is in our near future. And you want to know exactly when, and we don't know. But the main message is that earthquake, a big one, potentially 7.4, happened in eastern Washington on a fault very similar to faults that are all through this area in Ellensburg. So let's look at that too. To the visuals we go. Okay, let's go ahead and jump in. We need the visuals, right? The chalkboard only gets us so far. Let's go to some visuals. So we leave Ellensburg. You are here. And we're going here. Look at that. Look at how long and thin that lake is. Kind of looks like Roosevelt, kind of looks like Banks, but we know this is a different story. This is a glacial story. Yeah, take US 97, get over to the Columbia River, head up to Chelan. Why not? There's all sorts of reasons to go up there. It's a vacation place. People have second homes. They have third homes in the Chelan area. Look at that. Why wouldn't you go to a lake like this? Oh, sure, we can go drink beer. We can drink hard cider. We can do winery tours, etc. We can play a little golf. There's all sorts of reasons to come to this area. And the town of Chelan is on the down lake side. There's a long history there. And if you can work your way along the shore, you can only drive along a portion of Lake Chelan. Look at that history, going back with agriculture and orchards and irrigation and power, and electricity. So the Chelan fruit is still a big part of the Manson area on the lower lake edge. Chelan fruit all over the place. The Apple Cup Cafe, why not? Drop in and have a little cup of joe in Chelan itself. And all these beautiful old fruit labels, I'm a fan of those in general, but the Lake Chelan area has that in spades. If you want to jump on a boat and go all the way up to the head of the lake, 50-mile journey, you can do that and get up to Stehekin, get yourself through the Narrows, and learn about the shorelines and watch how the shoreline changes. Up at Stehekin, the landing is there. It's a point of entry to the North Cascades. And you bet, recreation, boat docks, complicated rocks, and why not look at a few beautiful scenes from Lake Chelan itself. Fresh water, deep lake, you betcha. Oh sure, I got some money, I live in Seattle, I'm tired of the rain, I'm going to spend weekends over in Chelan. I got my own dock, and my neighbor, we've all got boats, we're going to just party up there, man. That's the scene, Lake Chelan. But we're here to talk about the geology, not that other shenanigans. And the geology is on display wherever you look. And as we've already talked about with the chalkboards, way more than the glacial story. Chelan, the town, the narrows, landslides, and working our way up the lake. It's a desert today down the lake, the low end of the lake. There's sagebrush, and that makes it nice for us. Here's that dam. It's not a big one. And remember, this only raised the level of the lake 20 feet in the 1920s, probably mostly for irrigation, although I'm really making that up. But there was a deep lake long before this dam was created. All right, good. That's the setting for Lake Chelan. Now, is the lake glacial like Wallowa Lake, which is in northeast Oregon? There was an alpine glacier that came out of the Wallowa Mountains, and look at this beautiful moraine. This is what I was trying to draw on the chalkboard, which is not the case for Lake Chelan, but I guess most people would assume this might be the case, that you have a lake from a glacier, the ice pushed its way down, alpine ice, the ice melts back, and the water is trapped behind a moraine. That's common for lakes created by glaciers, but that is not the story for Lake Chelan, right? Let's slow down and look at this very carefully. So the town of Wenatchee is here. You're like, where's Lake Chelan? It's not on the map. This is a map during the Ice Age, and Lake Chelan is under this ice. What is this ice? Ice sheet from Canada masquerading as an alpine glacier. So can you see that the portrayal of this ice sheet is different than the portrayal of these individual little alpine glaciers? I know they're all white, but hopefully you can see they're showing this different than this. That's a main part of tonight's lecture. Alpine ice making dinky little lakes, making dinky little moraines, major ice sheet arm and major ice sheet arm, and the battle of the two arms to dig and form a basin that is hundreds of feet below sea level. Look at that sheer wall. Ice sheet cutting as opposed to alpine cutting. And multiple advances and retreats. I keep saying that, but that's important to remember. It wasn't just one advance and retreat of the ice. We got 2.5 million years to play with. This is a brand new figure from John Riedel, the guy who I mentioned from North Cascades. We'll meet him momentarily. And I love this map. I hadn't seen it until last night. He just emailed it to me generously. And here is the terminal moraine, which is on the southern margin of Lake Chelan. And you can see again, we're having the continental ice invade the Cascades. Now, what does that look like? Hopefully this works for you. This is a classic North Cascades shot. I just snapped this out of an airplane window as we were approaching Seattle from the east. And each of these little valleys had an alpine glacier in it. So it's a U-shaped valley, and I want you to pay particular attention to these ridges. Look at how razor sharp these ridges are. That's normal. These are called arêtes, steep razor sharp ridges from alpine glaciers carving, and a next door neighbor and a next door neighbor, and they're all carving multiple times. But John says, if you're thoroughly wide awake in the North Cascades, there are plenty of ridges that are not razor sharp. They're beveled off. They've been rounded over. Something crossed the razor sharp ridge and screwed it up. And photos like this are all through John's presentations. John Riedel from North Cascades National Park. Look at this. Ice flowing, ice sheet flowing from left to right. Ice sheet sculpting this formerly razor-sharp ridge and beveling it over. This is ice sheet crossing divides, and eventually it's this ice sheet that's going to find its way to the Chelan Valley. The Chelan River Valley that no longer has a river in it, it's got a lake. Now, in addition to those beveled ridges, which I just love, of course there's glacial till. Of course there's rocks that are big and loose, and they were transported only by glacial ice. But this could be alpine or continental. It doesn't have to be continental. This is how thick the glacial till is right above dropping into Lake Chelan. And there's an Ice Age flood story I want to mention briefly here before we quit. Don't let me forget that. So more glacial till, mostly Cascade rocks here. Now, if we're hiking up above Chelan, the town, this is the Chelan Butte area. My wife and I were up there over Veterans Day weekend just a couple months ago and didn't really know what we were doing, but we just found a public trail and just started wandering. It's a great trail, kind of like Menashtash Ridge here in the valley. Lots of people on it on a holiday weekend. But notice how sculpted Notice how weird this face looks. This is almost like somebody dragging their fingers along the side of a stick of butter. It's the ice that did that. It's the Canadian ice sheet that did that and sculpted these hills above Chelan. To us in geology, that just screams glacial activity, more than the lake itself. This sculpted landscape and the steepness of those slopes. And then, of course, all this glacial till, all these loose rocks that are up there on tops of the ridges. How'd they get there otherwise? You don't normally get piles of loose rocks on top of ridges unless you have a thick glacier leaving rocks that were brought in from elsewhere. You starting to see the picture now? Isn't it handy to have actual photographs instead of a caveman drawings on a chalkboard? That only gets us so far. Again, the sculpted, this is mostly erosional in my interpretation, but there's also some cave terraces up there as well, some little deposits along the former margin of the ice. Right, we go 386 feet below sea level, the floor of Lake Chelan itself. That's a deep sucker. Now, the idea that I forgot to mention, and I actually forgot if I have a slide for it, but I just want to throw it in case I forget. There were times that the masquerading ice sheet, you know what I mean, and the ice sheet coming up lake didn't touch. And there was actually times where we had water between both arms of the continental glaciers, water in the trough that had nowhere to go. And the water was ponded higher and higher until that glacial Lake Chelan, this body of water halfway in the trough, was 700 feet above its current level. If you get water that high in that trough, you're going to have spilling. You're going to have an ice age flood. Water in glacial Lake Chelan spilling to the south. Do you know Navarre Coulee or Knapp Coulee? They have roads in them today. Those are two roads you can get to the lake. Those roads, those coulees, Navarre Coulee and Knapp Coulee, had ice age flood water coming down, which is basically glacial Lake Chelan water spilling to the south. Pretty cool. Now, the evidence of how we know the ice pushed in from the east as well as from the west, what's the evidence? We crossed this brown stuff, which many of you know is flood basalt. These are lavas that happened millions of years before the ice age, and the cracks are here. The lava came out. It was orange syrup, essentially. And notice that Chelan and Lake Chelan are not in that basaltic scene. It's to the east of the lake. And if you get up on the Waterville Plateau, there's wheat fields. It's like a different country. And you're right next door to the Columbia River. Why? Because you're on those basaltic plains, essentially. Why is that important? Well, here comes our ice sheet from the east, the Okanagan Lobe, and it's going to approach Lake Chelan from the east, remember? And what's the significance? It's going to pick up German chocolate cake chunks, basalt. It's going to carry those basalt chunks into the Chelan Trough and drop them. Glacial erratics that are basaltic, like these guys. This is Jaeger rock. We're still up on the Waterville Plateau, but I want to give you some photos of some classic basalt glacial erratics that the ice sheet picked up and moved just a few miles and then dropped up on the Waterville Plateau. But what happens if you have that ice, pick up the basalt, head west, cross the Columbia, and enter the lower part of Lake Chelan? This best photo I got for you tonight. Do you like it? This is McNeil Canyon. We're just across the Columbia River from Chelan. We're to the east of Chelan. And these are the beautiful basalt glacial erratics. They look like they were just let down on a string from heaven, don't they? They didn't come from heaven. They came from the Okanagan Lobe. The ice from the east brought these guys in. And if you're in the lower part of Lake Chelan and the hills above the lower part of Lake Chelan, there's many more of these basalt rocks. If that's not enough for you, look at the thickness. We have 400 feet of glacial rocks, loose glacial rocks, under the town of Chelan. This is all from the Okanagan Lobe as well. This is also from the arm of the ice sheet coming in from the east. Who knew? Not me, certainly, until I went on John Riedel's field trip a couple of years ago. That pile of 400 feet of Okanagan drift, we call it, has been cut more recently by a little Chelan river that only goes a couple of miles and takes a little bit of water from the basin and gets it down to the Columbia River. Okay, we have it now, the ice sheet story. I hope you do. Here's our lake. White is all the ice sheet from Canada. Hope you're feeling good about that. Way more than you probably had 45 minutes ago. At least I'm hoping that's the case. Let's meet John Riedel briefly in this beautiful little artsy film and get a sense of what he's about.
Glaciers are elders of the landscape. The rhythms of the mountains recorded by glaciers are cycles of climatic change. They are the annual rhythms of seasons, climatic cycles spanning tens of thousands of years, the ultimate force shaping the mountains and causing change to land and life. Despite this power, the rhythms are imperceptible, the beats slow and complicated, but inexorable. They can be seen and heard only by those who take the time to look and listen for them. I have had the privilege and the resources as a geologist to listen and learn.
John Riedel, neat guy, from Wisconsin. You can't be all bad if you're from Wisconsin, right? All right, there is a little bit of Ice Age flood story I'd like to touch on before we leave the glacial action. When the Okanagan lobe is there, and we know its role now, it's helping to form it's helping to form Lake Chelan, the Missoula floodwater coming across Washington is not allowed to get to Chelan when this ice sheet is in place. And so the Missoula floodwaters are diverted to cut the Grand Coulee. The Missoula floodwaters are diverted over Dry Falls. The Missoula floodwaters get ourselves down to Quincy Basin. So many of you know that story. It's interesting to lay this story in. This is happening basically at the same time. Each time we have the Okanagan lobe. But when we finally melt the Okanagan lobe back, we can get a few at least Missoula floods coming all the way down the Columbia River, and those Missoula floods are coming right near Chelan. Not over Chelan, but down the Columbia River at Chelan. So Missoula floods cutting the Grand Coulee, Missoula floods cutting the Grand Coulee when the ice sheet is there. When it's not, we can have the Ice Age floods come down the Columbia. This is a nice map from Jennifer Hackett, again showing our ice sheet, Chelan, Lake Chelan under the ice. And this is the map of the Columbia River in between Ice Age flood events. And the Columbia River went Coulee City, Moses Lake, almost Othello, around the north face of the Saddle Mountains, get to Beverly, hang a left, and then continue down the Columbia Valley that we know and love today. This is Ice Age floodwater coming down over Wenatchee. Again, we need the Okanagan lobe out of the way. Those beautiful Missoula floods coming down the Columbia, they were monster floods, leaving giant current ripples like this downstream from Wenatchee. But back up in the Chelan area, this whole Columbia River scene is right next door to Chelan and Lake Chelan, just off the frame to the left. Okay, transition time. Let's go to the bedrock. Now look at this bedrock. These are grad students. Their first experience they have when they show up to study here as graduate students here at Ellensburg at our department, Central Washington University. They're coming from all different parts of the country, and we take them out in the field right off the bat. It's Labor Day-ish, and we take them out, and sometimes those field trips last a long time. They age quite a bit by the time they're done with that experience, but they learn a lot. That's what's important. Map from Eric Cheney to show a simplified flood basalts. And now we realize, look at the jigsaw puzzle. Look at these blocks that all have their own story to tell. I mean, I wish I could do more. And part of it is me being limited in my knowledge, and much of it is we still don't have a basic story figured out for all these little pieces. Maybe someday, but not now. Well, now we're interested in the rocks, and we're interested in the migmatite and the schist. So there are places where there's not glacial till, but there's actual bedrock popping out of these ridges. And that's where we go now. Aha, migmatite. Swirl. Swirl. Mixture of what? Migmatite? That's right, igneous and metamorphic rocks. Look at that. Are you kidding me? Can you think of a place in Washington that has more beautiful, complicated rocks that are so accessible? This is driving right up 97, or 97 alternative if you are alternative. Yeah, it should be more of a swirl like that when we really start looking at the details of these migmatites. So this is from a field trip led by this fellow Chris Mattinson, who I work with here at the college in Ellensburg. And he is an authority on this migmatite, and he has done a beautiful job of piecing a lot of this history together. And I feel confident with the Chelan migmatite complex, mainly because of my learning from Chris directly. And he continues his work. Remember, he's the guy that's going to try to link the Okanagan batholith, or the Okanagan granite, with the Chelan migmatite if the data allows. So here's Chris in action. Look at charts like that. Look at how complicated. Look at how swirled. Look at how there's like multiple generations. But remember the main point? These are rocks that were in the deep crust. This migmatite was developing and forming, I'm not exaggerating now, 18 miles below the surface. This is where the sausage is being made. This is where the magmas are first being developed before we push that magma up into a magma chamber. And that migmatite, that deep rock, had to eventually get back to us, right? Had to be lifted 18 kilometers. And we've got good evidence that that deep crustal migmatite in the Chelan area was brought way back to the surface, 18-mile journey, and got up here by at least 50 million years ago because of those plutons, those granites and those dikes that are cutting through at shallow levels. So look at the complication here. This is my sketch I was trying to make sense of. Chris gave us these photos of just one outcrop with these, this is where they put the dynamite in to blast a road cut. This is just north of Chelan on 97 on the way up to Pateros. And you can spend hours just trying to piece that story together. Just relative age dating. Which of these is first, second, third, fourth, fifth? And again, you're trying to reconstruct this whole sequence 18 miles below. There's another outcrop. This is, do you know this road? This is going from Columbia River, climbing up to the town of Chelan, and this beautiful face, which wasn't there until, I think somebody said in the 50s or 60s, but I don't really know. Anyway, a beautiful face that is one of the best outcrops in the state, especially for learning about complicated metamorphic rocks like the migmatites. And then along the lake itself, dying light of the day on a hot September day, and Chris is still at it with all these details in the migmatite itself. Gorgeous stuff, wouldn't you say? You can appreciate it at least visually, if not geologically. That's kind of where I am today. I still don't have a whole lot figured out about the details, and very few people do. You got to be pretty bright to read each of these metamorphic minerals and come up with certain temperatures and pressure conditions. So we'll just stand back and be at awe with all these kinds of cooling histories and pulses of magmatism and metamorphism from this migmatite. Hey, a pen from CWU for scale. All right, there's different pulses of action within this migmatite. The big message is the protolith, or the original rock that was then squirreled up and swirled up at deep levels, has been dated at 165 million years old. That's way older than these other terrains in the neighborhood. So compared to its neighbors, the Chelan migmatite complex is not only deep, but impressively old compared to its neighbors. And what does that tell us? Does that tell us that this is somebody else's crust, in other words, an exotic terrain? Or does that mean this is originally some stuff in Washington that has been swirled up? Unclear to me, unclear to most at this point. Thank you, Chris, for these diagrams. Wish I understood everything in them. I'm sharing them anyway. Nice teaching choice, right? Teaching stuff you don't even understand? Great. I will say one more thing about the migmatite. You can take a grain of zircon. A zircon is a mineral. You can take a grain of zircon that's the size of a sand grain, And you can, with techniques that now Chris has mastered and instrumentation that Chris now has in our new science building, and drill holes essentially in this little grain of sand. Again, it's a zircon from the migmatite. And you can get different ages from different portions of that little grain of zircon to then tease out different changes, different times of metamorphisms, different parts of the history of that swirled rock. Staggering. Thank you, Chelan Migmatite Complex. We're moving on. So Chelan, that's the migmatite. Here up by Brewster is this granitic rock. Remember the chalkboard sketch? Maybe this is the magma chamber and this is the plumbing system below the magma chamber, and maybe they're lying on their side along the Columbia River between Brewster and Chelan. Let's go to a couple other neighboring blocks and then we'll transition with the final comments we have for the earthquake story. This is the Napiqua complex. It's a schist that's just to the south of the Chelan migmatite. It for sure is an exotic terrain, interpreted as sediment that was originally on the floor of a deep ocean and was somehow transported from a deep ocean to the area of Eniat, just south of Chelan. Now, how do you do that? You take stuff on the ocean, you convert it into rock, number one, then you get a metamorphic rock, number two, then you somehow get it into interior Washington, and oh, by the way, a few thousand feet above sea level. Good Lord, there are stories to tell, and that's the complication and that's the intrigue of these very impressive swirled rocks as well. This is just up the Eniat River from the Columbia, if you're interested in seeing this, right along the road. Finally, the Swakane gneiss, the Swakane biotite gneiss, which is further south yet. Now we're approaching Wenatchee. This is also available along the Columbia, and this is interpreted as sediment, sand primarily, that was originally deposited in an oceanic trench. Again, it's got to be a terrain. It was originally out in the ocean somewhere in a deep trench. We take that sediment, we convert it into gneiss, and we get it here to central Washington. Am I blowing your mind? Have you heard about this terrain stuff before? Boy, if I ever get gutsy enough, we'll do a bunch of lectures on these, but boy, you really have to eat your Wheaties to put this all together. Swakane biotite gneiss. Some granites up there. I think we're done. Oh no, we got one more thing. So cutting through all of that old rock are these dikes, these feeder dikes that I got really intrigued by when we were on the trip in September. Here's it, feeder dike, cutting across. 50 million years old, roughly. 50, much younger than the rocks themselves. So we have to crack these rocks somehow and send these squirts of mostly dark-colored stuff up through them. We call it a mafic feeder dike. And some of you are nodding your head because you know about mafic feeder dikes. There's mafic feeder dikes north of Ellensburg in the Liberty area. There's mafic feeder dikes that are much younger in the Columbia River basalts of southeast Washington. The point is, these mafic dikes are the same age and potentially the same composition as the feeder dikes in the Liberty area. I'm not saying there's gold here, but I am saying that there is a more regional extent to these Eocene feeder dikes that I didn't understand before until last September. Even this famous place called Ribbon Cliffs, which we're going to talk about in just a second, has ribbons in it because these are the mafic feeder dikes that appear to be part of the same feeder dike story of the Liberty area. Brand new to me, by the way, maybe to you too. Feeder dikes in the Teanaway and all these feeder dikes with about the same orientation, a northeast orientation, up through the Chelan area. See, this is close to home. This is us, Mount Stewart and these feeder dikes cutting through. We've already talked about those in previous lectures. These feeder dikes coming through the Stewart batholith. I'm saying the feeder dikes up by Chelan potentially are the same story. Oh, by the way, you can take some of these terrains and cut them in half. It's not enough that they come in from the ocean. Once you get them here, let's cut them up again, and let's send some of them further north. Good Lord. Oh, I can't even look at that. I'm getting a headache. There are books that help, general audience books. Geology of the North Cascades is beautifully written by Ralph Haggerud and Roland Tabor, and I highly recommend it. It's more than 10 years old now, but it's still beautifully done to at least make a first attempt at saying some regional things about the North Cascades. Okay, the last section of our lecture is talking about earthquakes. This is Seattle in 1949, but I want to talk about a bigger earthquake than this. The earthquake that happened in December of 1872. For many years, you would just travel along the Columbia River north of Wenatchee, heading to Chelan, and some of you on the west side of the river, you would know this place called Earthquake Point. And they would talk about, again, Ribbon Cliffs, where this is where a mountain broke in half. And half of the mountain fell and slid into the Columbia River in 1872 due to an earthquake and blocked the Columbia River. And there are Native American accounts of that actually happening. And in the river are still major blocks of that slide, that landslide, where half the mountain broke and fell. Here we've got it. Can you see it? Mountain, half is too strong, but a portion of the ridge broke and kerplunked. And this is before dams were on the Columbia River, of course, and so the river was dammed. Oh, we got somebody jet skiing on a hot summer day right in front of the broken face. It's this where we have the most exciting evidence of this earthquake, but this is not where the fault is. This is not where the ground actually broke and all the seismic energy came away. It must be close to this, perhaps, but not the actual fault. That was the mystery for so long. This is a map basically estimating a magnitude of 7.4 and a map from all the general newspapers at the time recording what people experienced across the Pacific Northwest. Again, to try to find where this earthquake actually happened. Where was ground zero for this big earthquake in eastern Washington, if it was in eastern Washington? This is an account, I'll read you just part of it, from Thorpe, which is just a little town outside of this town of Ellensburg. This guy says a severe shock of earthquake is being felt this morning, in other words, an aftershock, but the last night at 10 o'clock, old Mother Earth was being shaken from the west to the east, not true, it turns out, throwing all the poultry from their roosts, frightening the dogs, cats, horses, cattle, stopping clocks, jarring chimneys from their foundation. So that's in our valley, this guy experiencing that. In Walla Walla, a low rumbling noise was heard, rattling windows, swinging picture frames. In Yakima, the earthquake at that place was quite severe. There were 3 distinct shocks. The Indians on Rock Island near Wenatchee say the mountain at that place rolled down and killed 3 persons. That's probably Ribbon Cliffs. Snoqualmie Pass, people were shook off their feet. They were standing at Snoqualmie Pass. They were knocked to the ground. In Yakima, people rushed out of the doors in a great state of alarm with clubs, revolvers, and shotguns, thinking the Indians had made a general attack and were tearing up things generally. All right, let's continue. Windows shattered in Victoria, BC. Chimneys cracked in Olympia. Trees toppled in Puyallup. Dishes crashed in Seattle. And my personal favorite, a lighthouse near Port Angeles rocked to and fro most alarmingly and was severely damaged. Where the hell is this earthquake? Is it really 7.4 magnitude? Did it really happen in eastern Washington and affect all these regions? Felt as far away as Northern California? Again, that was the mystery for 100 years and more, from 1872 until just a couple years ago. So for many years, all geologists could do was to say, well, probably up in the Chelan area, probably in that circle, based on these reports and a couple of basic field observations. But that circle persisted for many years, and of course, every generation you'd have an enterprising kind of youthful geologist going, I can figure this out, I can find this fault. We got to find this thing, man. And as I mentioned, just 2 or 3 years ago, Brian Sherrod from the USGS, who has a new tool that previous geologists did not. He has something called LIDAR. Some of you know about it. You have these beautiful images of the land surface, and you can magically remove all the vegetation. You can remove everything, and you can get a very detailed image of what the ground looks like. And Sherrod started looking, sitting at his desk in his office, started looking at all these LiDAR maps, these LiDAR imagery sets coming in. And he was actively looking for places where it looked like there was a fresh break in the ground. And he found a place that was worth investigating. It's a place called Spencer Canyon. So we are looking west across the Columbia at Orondo. Can you picture where that is? Let me help you out. So here's the town of Waterville. We're on US Highway 2. We're dropping west down to the Columbia. That's quite a grade that you go down. And then most of us hang a left when we get to Orondo and follow 97 down to Wenatchee. I'm saying across the river from Orondo, across the Columbia River, this little canyon, Spencer Canyon, there's no road in there, is where the ground broke in 1872. It's rugged. So Sherrod and a few of his buddies, including a guy that lives in town here, John Lasher, who is here tonight, got in on foot and maybe some old four-wheel drive vehicles up into Spencer Canyon. So this is Lasher taking a photo in rugged Spencer Canyon, looking back now to the east. You got your bearings? Orondo, the river's right down here, and here's US 2 climbing to Waterville and eventually Coulee City. You got it? So using the LiDAR from Spencer Canyon, a scarp, a place where the ground was suddenly broken clean, was identified. And that LiDAR, you can imagine how much LiDAR you need to go through. You're looking for a needle in a haystack, essentially. But that scarp was found. It looks like this in the imagery. So that's not enough evidence. You just see a little crack. So you got to go there. And you got to dig a trench. You've got to dig a trench. You actually literally have to dig a trench perpendicular to the trace of the scarp and try to find some layers that you can date. If you know the ages of the layers that have been broken, you can say something about how frequently the ground is going. Look at this thing. And again, this attracted Sherrod. This is a landslide. Looks pretty darn fresh. The ground broke here, and this material flowed potentially in 1872, says Sherrod. So we not only have a scarp that's pretty fresh, but we have at least one debris flow of some sort. So just to put this in general context, we're talking about shallow earthquakes now with this 1872 event. We're not talking about magnitude 9. We're not talking about deep things like Nisqually or 1965. We're talking about shallow crustal faults, the most famous of which is the Seattle Fault. But if you get over to eastern Washington, some of those shallow crustal faults exist as well. And it turns out the area between Wenatchee and Chelan has been very seismically active in the last 150 years. No killer quakes. This is the 1872, by the way. The bigger the circle, the bigger the earthquake. But notice how many moderate earthquakes have been in what's known as the Chelan seismic zone. If you talk to somebody born and raised in Eniat or Orondo, they have many little shakes that they can remember. And if they're a fan of seismic stations, there are thousands that have been recorded, but too small to feel. Why are all these earthquakes happening at shallow levels? The real basic message is Washington is getting crunched. It's getting squeezed between western Washington generally moving actively to the northeast against this portion of Washington that's basically not moving very well. So you've got slamming against non-moving, and you've crunching this kind of general zone. Here's an animation to help you see that. It's going to go in motion in just a second. The motion of the Pacific Plate and the Juan de Fuca Plate are driving this clockwise rotation of the crust from California to western Washington, and all of that is moving against stable northern Washington. As a result, we keep having these shallow crustal earthquakes like the 1872, and the potential is to have something that big again. Again, yellow dots are earthquakes. Look at this cluster between Wenatchee and Chelan. And the biggest circle, again, is our 1872 quake that was a mystery. We've got faults, by the way. These are reverse faults that are developing these earthquakes. This is south of Ellensburg on the way to Yakima. So, boy, there's some history of earthquakes in eastern Washington, and we are just starting to comprehend the significance of them. I don't want to freak anybody out. We don't have enough dates to be able to predict how frequently these earthquakes happen in eastern Washington, but the potential is there for more concern than we have now, let's put it that way. That fault was just on the way to Yakima. Okay, finishing up, I promise. You maybe had about enough, and let's wrap it up. So up in the Lake Chelan area, we're squeezing the crust. That's responsible for this. Let's actually get into Spencer Canyon and see what that scarp looks like up close. It's right here, running across the side of the hill. And in the general area, there's some more of this ribbony, cliffy stuff, these Eocene feeder dikes, but that's not part of the earthquake scarp itself. Instead, look at that. That's where the ground broke in 1872, on that winter night after 9 o'clock, on December whatever, 1872. And to build the trench, to dig the trench, it was too steep to get any sort of bobcat or any sort of backhoe up in there. So a bunch of these guys, these geologists with all these advanced degrees, grabbed a bunch of shovels. They dug a trench by hand. And they needed that trench. Brian Sherrod, the leader of this little organization, and John Lasher, who lives in town here, who was a citizen geologist to help out. He's also good with heavy machinery, although they couldn't use it on that occasion. They dug this by hand, and they needed to find layers underground that were clearly broken by this scarp. And then if you get the ages on the layers, you can say something about when the ground broke, or if you had repeated failures. So this was exciting to many of us because a mystery has been solved. Not why the earthquake happened, but where the earthquake happened. We actually finally have the smoking gun for the big, quote-unquote, Chelan earthquake of 1872. It wasn't in Lake Chelan itself. It was to the south in Spencer Canyon. So thanks to Brian Sherrod and Harvey Kelsey and a few others that were involved in that work. So we've got all sorts of things. Hopefully Jerry is pleased by now. We've got the lake, we've got the rock types, we've got the terrains, and we have this fault in Spencer Canyon putting a little cherry on the top of the cake, or whatever the analogy is. We thank you, Lake Chelan, for all of your wonderful geology, and I thank you all tonight for coming. Thank you very much. Appreciate it.